Let's talk about projectile motion. So, in that horizontally launched projectile FET activity that you guys did last week, you should have seen that the only thing that affected the time that it takes a horizontally launched projectile to hit the ground is the height that it's launched from. Now, the reason that this is important is because we saw that the horizontal velocity at which that cannonball was fired didn't affect the time that it took to hit the ground. So, what this tells us is that the vertical motion and the horizontal motion, or the Y motion and the X motion, are completely independent of one another. Now you can see a picture right here. It doesn't matter if this ball is dropped or if it's shot out to the right, it's going to fall at the same rate as long as it is dropped from that same height. So again, if we're given a horizontal velocity, it doesn't even affect the time that it takes the ball to fall. So which will again tell us that the horizontal motion and vertical motion are completely independent of one another. Now this ball that's shot out right here, it's undergoing the same amount of force that this other ball is that's being forced downward because they're both under the influence of the force of gravity, right? So the only acceleration that's happening here is in the Y direction, pulling down on both of those balls, making them accelerate towards the surface of the Earth at 9.8 meters per second squared. This one that gets projected outward, it does have some horizontal motion as well, but there are no forces acting in the horizontal direction. So the only reason it keeps moving is because of the ball's inertia, which we'll talk a little bit more about when we talk about Newton's laws in our next unit. But basically, Newton's first law says an object in motion will stay in motion. So because there's no outside forces acting on this yellow ball as it goes down in the horizontal direction, it's just going to continue with its horizontal direction at constant velocity. So since we know that there is a force acting in the vertical direction, which is causing that acceleration of gravity, right? The force of gravity pulling those balls down, causing an acceleration downward of 9.8 meters per second squared. And then there's no forces acting in the horizontal direction. So therefore, we're going at a constant velocity in the horizontal direction. So because of those two things that we know, acceleration in the Y direction, no acceleration in the X direction, we can now apply some equations that we already know to these two motions and make them completely separate of one another in order to do these problems. So projectile motion, we have two-dimensional motion. Horizontal motion and vertical motion are independent of one another, which means that neither motion affects the other motion, which we saw from that horizontally launched projectile FET activity. What we're going to do is we break up two-dimensional motion into two separate one-dimensional motions, meaning the motion in the horizontal X direction with no acceleration and the motion in the vertical Y direction with a constant downward acceleration, which is the acceleration of gravity, or 9.8 meters per second squared. Now, the thing that we are going to relate these two things with is time, because no matter what, if we have just one-dimensional motion up and down, or if we have this two-dimensional motion, we're still talking about this one object. So in that two-dimensional motion, even though we break up the X and Y directions, it's still talking about the same object and the same motion, so we can relate the two with time. All right, so let's talk about the equations. So in the X direction, which is the horizontal direction, we have no acceleration because there's no force in that direction. So because of that, velocity is constant. So we're going to use the constant velocity equation. Velocity is equal to displacement over time. Notice how I have a sub x, all right? What this means is velocity in the X direction is equal to displacement in the X direction divided by time. Now we call this delta x the range, which just means the farthest that the projectile travels in the X direction. Now for the Y motion, which is the vertical motion, we have a constant acceleration in that direction. So because of that, we're going to use the constant acceleration equations. Now we know these three equations, of course, you have a couple more, but these are the main ones that we're going to be using. We have our change in position in the y direction is equal to the initial velocity in the y direction. Pay close attention to these subscripts right here, okay? Because it is very important for us to split up the velocity and have both the y component and the x component of velocity. So we have the initial velocity in the y direction times time plus 1/2 times the acceleration in the y direction times time squared, where of course this acceleration is the acceleration of gravity. And then we have final velocity in the y direction equals initial velocity in the y direction plus acceleration times time, and then final y velocity squared equals initial y velocity squared plus 2 times the acceleration times the displacement in the y direction. Now we talked about this when we talked about free fall motion, that vertical motion as something's falling through the sky. Just remember that you have to be really careful with your signs here. Usually we will call down positive. Of course, that's just a notation, so you can call whatever direction you want positive, but as long as you're consistent, it'll be fine. Now, I told you guys that we need to split up our x and y velocity. So what I mean by that is if we get velocity being launched at an angle, so say, a cannonball is shot out of a cannon at an angle of 20 degrees and a velocity of 100 meters per second, they're giving you the hypotenuse of this velocity and the angle. So what we need to do in order to split up the horizontal motion and the vertical motion is we need to use our trigonometry in order to do that. So we know that this velocity in the x direction right here, that is the adjacent side to the angle. So we'll use cosine. So we can see that the initial velocity in the x direction is equal to the velocity, which whatever that launch velocity, times the cosine of the angle. And then in the y direction, we can see that this is opposite that angle. So the angle, sine of the angle will be the v initial y over v. So the initial velocity in the y direction will be equal to that launch velocity v times the sine of the angle. Remember this naught right here, v sub naught x, v sub naught y, that means initial. And here, a lot of the time when I do these problems, you will see that I will just write v sub, I'm sorry, my dog's barking. I will just write v sub x, all right? Because remember, the velocity in the x direction is constant.